In absolute darkness, 13 billion years ago, something impossible is glowing. 300 million years after the universe exploded into existence, giant spheres of hydrogen are shining across the infant cosmos. But they should not exist yet. These are not stars as we know them. They burn without fire, powered by something invisible, tearing itself apart inside. NASA's James Webb Space Telescope has found them, and they rewrite cosmic history. If you enjoy discovering the universe's deepest secrets, hit that subscribe button. We're going deep tonight. Prepare yourselves. The first dark stars are waiting in the ancient void. The James Webb Space Telescope aimed its instruments at a patch of empty sky and found something that should not be there. Scientists expected darkness. They found light blazing from a time when the universe was barely 300 million years old, when nothing should be bright enough to see across such vast cosmic distance. These objects glow with impossible intensity, appearing as tiny red dots scattered across the ancient heavens. Every astronomer knows the timeline. First comes darkness, then hydrogen clouds collapse under gravity. Nuclear fusion ignites. Stars are born. But these glowing objects exist before that process could happen. They shine from an epoch when the universe was still cooling, still organizing itself, still figuring out how to make the first generation of anything. The telescope captured their light after it traveled for over 13 billion years, crossing an expanding universe to reach our detectors. Catherine Fries, a physicist at the University of Texas, studied the images with growing excitement. She had predicted these objects back in 2007, calling them dark stars. For years, her theory waited for technology capable of seeing that far back in time. Now, the evidence was appearing in data streams from the most powerful space observatory ever built. What she found matched her calculations almost perfectly. The objects appear red because of cosmic expansion. As space stretches, light stretches with it, shifting toward longer, redder wavelengths. The more distant something is, the redder it appears. These dots rank among the reddest objects ever detected, placing them in the universe's extreme infancy. But their brightness defies explanation using conventional stellar physics. Fusion-powered stars cannot form this early. The process requires specific conditions that did not exist yet. Heavy elements had not been created. Cooling mechanisms that allow gas clouds to collapse were absent. The cosmic environment was too hot, too chaotic, too pristine. Something else must be generating this light, something using a completely different power source. The telescope's spectroscopy instruments measured the wavelengths of light coming from these objects. One target, labeled with a technical designation, showed an absorption feature at 1,640 angstroms. This signature does not appear in normal galaxies. It suggests something exotic, something never observed before in cosmic history. The pattern matches theoretical predictions for objects powered by dark matter rather than nuclear reactions. 4 candidates emerged from the initial survey. Each one existed between 300 and 600 million years after the Big Bang. Each one displayed characteristics inconsistent with being a small galaxy filled with regular stars. Their temperatures were wrong, their sizes were wrong, their spectra were wrong. Everything pointed toward a new class of celestial object that cosmologists had theorized but never confirmed. The discovery sent ripples through the astronomical community. If these objects are truly dark stars, they solve multiple mysteries plaguing our understanding of cosmic evolution. They explain how supermassive black holes formed so quickly. They explain why early galaxies appear brighter than predicted. They might even reveal the nature of dark matter itself. But what makes a dark star shine? The answer lies in something invisible, consuming itself deep inside massive hydrogen clouds. Picture a cloud of hydrogen and helium floating in the early universe, stretching across distances that would take light weeks to cross. Inside this cloud, something strange is happening. Invisible particles are colliding with incredible violence. tearing each other apart and releasing massive amounts of energy. This is not fusion. This is annihilation. Dark stars are theoretical objects that Fries and her colleagues proposed almost 2 decades ago. The concept is straightforward but revolutionary. What if the first luminous objects in the universe were not powered by hydrogen smashing together to make helium, but by dark matter destroying itself? The energy released could heat a gas cloud from within, making it glow without ever compressing into a dense stellar core. These objects would look nothing like the stars we see in our night sky. A normal star like our Sun has a nuclear furnace at its center, surrounded by layers of progressively cooler gas. All the energy comes from that tiny, incredibly hot core. Dark stars work differently. Their energy source is distributed throughout their entire volume, wherever dark matter particles happen to meet and annihilate. Think of a regular star as a bonfire, with all the heat concentrated in one spot. A dark star is more like fog lit from within, glowing evenly throughout its enormous structure. This fundamental difference means dark stars can grow to sizes that would be impossible for fusion-powered objects. Without a concentrated core fighting against gravitational collapse, they can swell to truly monstrous proportions. Confirmed observations from JWST show objects that match these predictions remarkably well. They are puffy, diffuse, and incredibly luminous. Their temperatures suggest they are not compressed enough for fusion to occur. Their chemical signatures show only hydrogen and helium, the primordial elements created in the Big Bang. Everything about them screams different when compared to any star we have ever studied. The theory requires 3 specific conditions to work. First, you need a region of space with extremely high dark matter density. Second, that dark matter must be capable of self-annihilation when particles collide. Third, the resulting energy must get trapped inside the hydrogen cloud rather than radiating away into space. In the early universe, all 3 conditions existed simultaneously in special locations called dark matter halos. Cosmin Illier, an astrophysicist at Colgate University, has spent years refining the mathematical models. His calculations show that dark stars could reach masses equivalent to 1 million suns, while shining with the brightness of 10 billion suns. These numbers sound absurd, but they emerge naturally from the physics of dark matter annihilation, combined with the unique environment of the infant cosmos. The breakthrough came when spectroscopic data from JWST revealed exact matches to predicted signatures. The wavelengths of light, the ratios of different elements, the overall luminosity, everything lined up. After years of waiting, the theory had observational support. But finding potential dark stars raises more questions than it answers. How exactly does dark matter annihilate? What type of particle is destroying itself inside these cosmic giants? The answers might finally reveal what makes up 1/4 of everything in existence. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic forces at all. For decades, scientists have detected it only through gravity, watching how galaxies spin too fast and clusters of galaxies hold together too strongly. Something invisible is out there, and it outweighs all the stars and gas we can see by a factor of 5 to 1. The leading candidate for dark matter is a type of particle called a WIMP, which stands for weakly interacting massive particle. These hypothetical objects would have mass somewhere between 10 and several hundred times heavier than a proton. They would pass through normal matter almost without interaction, which is why we have never caught one, despite building increasingly sensitive detectors buried deep underground. But WIMPs have one crucial property. They might be their own antiparticles. When a particle meets its antiparticle, both objects vanish in a burst of energy. The mass converts directly to other forms, according to Einstein's famous equation: 2 particles in, pure energy out. This process is called annihilation, and it is one of the most efficient power sources imaginable. In normal conditions throughout the universe today, dark matter particles are spread too thinly to annihilate with any significant frequency. They drift through space, occasionally passing near each other, but rarely colliding. The annihilation rate is negligible, but in the early universe, conditions were vastly different. Matter was compressed into much smaller volumes. Dark matter halos formed as the first structures to condense out of the cosmic soup, creating regions where dark matter density was millions of times higher than the average. Inside these halos, dark matter particles would collide constantly. Every collision between two WIMPs would release a cascade of energy. That energy does not vanish. It transforms into photons, electron-positron pairs, and neutrinos. The neutrinos escape immediately because they interact with almost nothing. But the photons and electrons get trapped, bouncing around inside the dense hydrogen cloud and transferring their energy to the gas. This heating mechanism is subtle but powerful. Each annihilation event deposits energy equivalent to the entire rest mass of both particles. For a 100 GeV WIMP, that is roughly 100 times the mass energy of a proton converted to heat with every collision. Multiply this by trillions upon trillions of annihilations happening every second throughout the cloud, and you generate enough power to make an entire star-sized object shine. The process is self-regulating. As the cloud heats up, pressure increases, counteracting gravitational collapse. The object reaches an equilibrium where gravity, pulling inward, exactly balances pressure pushing outward. Unlike fusion stars, which require extreme densities to ignite, dark stars can maintain this balance while remaining relatively diffuse. They never compress enough to start hydrogen burning because they do not need to. Confirmed mathematical models show this mechanism works for a specific range of dark matter properties. The annihilation cross-section must be strong enough to generate sufficient heat but weak enough that dark matter particles survive to the present day. The particle mass must fall within a certain window. The conditions must exist in regions where hydrogen is abundant but not yet organized into normal stars. All these requirements aligned perfectly in dark matter halos during the first few 100 million years after the Big Bang. The question is whether nature actually exploited this narrow window of opportunity. The scale of dark stars defies human intuition. Imagine an object so large that light takes several weeks to cross from one side to the other. Picture a ball of glowing hydrogen that could swallow thousands of solar systems. These are not stars as we know them. They are cosmic monsters that make our sun look like a grain of sand. A typical dark star could reach 1 million times the mass of the sun, while shining 10 billion times brighter. To put that luminosity in perspective, our entire galaxy contains roughly 400 billion stars, and their combined light output is just 40 billion solar luminosities. A single dark star could match a meaningful fraction of an entire galaxy's brightness. When you compress that much light into what is essentially a point source from cosmic distances, it creates the impossibly bright dots that confused astronomers when JWST first sent back data. The structure is completely unlike anything we see in the modern universe. Normal massive stars pack their mass into relatively compact spheres. A star 10 times the sun's mass might be 10 times wider. Even the largest known stars today are only about 1,500 times the sun's diameter. Dark stars dwarf them completely, potentially reaching 10 times the width of Earth's orbit around the Sunday. This enormous size comes directly from the distributed heating mechanism. Fusion stars compress until their cores reach temperatures of millions of degrees, enough to overcome the electromagnetic repulsion between hydrogen nuclei. That compression creates enormous densities at the center, while the outer layers remain relatively thin. Dark stars never undergo this compression. The heat from dark matter annihilation is spread throughout the entire volume, so the whole structure can remain puffy and diffuse while still maintaining enough pressure to resist gravitational collapse. Theoretical calculations show these objects could survive for millions of years, possibly longer, if they capture fresh dark matter from their surroundings. Unlike fusion stars, which burn through their fuel in a predictable sequence. Dark stars last as long as their dark matter supply holds out. In the dense halos where they form, that supply could be essentially unlimited. Dark matter keeps falling inward, gets captured by the star's gravity, and adds to the fuel reservoir. The brightness varies depending on the mass and properties of the dark matter particle. For 100 GeV WIMPs, a 1 million solar mass dark star would shine with exactly the intensity needed to match the observations from JWST. For lighter particles, the stars might be somewhat dimmer, but still extraordinarily bright by cosmic standards. The range of possible configurations all fall within the window that early universe observations are now revealing. But here is what makes this discovery truly staggering. These giants are not the strangest things JWST found in the early universe. The telescope detected something else, something that initially looked like tiny galaxies but might be something far more exotic. Astronomers call them little red dots, and they are rewriting our understanding of cosmic evolution in ways even dark stars cannot explain. What appears at first to be simple is turning out to be the most complex puzzle in modern cosmology. Dale Kachevsky at Colby College was analyzing JWST data when he noticed something wrong with the numbers. Small, intensely red objects were appearing throughout the deepest images, existing in an era when the universe was less than 1.5 billion years old. At first, his team assumed these were compact galaxies, dense collections of stars packed into tiny regions of space. Then, they looked closer. The spectra were bizarre. Gas was moving at nearly 1,000 kilometers per second around these objects, speeds that indicate something with tremendous gravity at the center. Normal galaxies do not show this behavior. Small galaxies, especially, should not have material whipping around at such extreme velocities. The motion suggested accretion disks, the swirling funnels of matter that form when material spirals into black holes. But if these were black holes, they were far too massive for their host galaxies. JWST found over 700 objects that might date from the first few 100 million years after the Big Bang. The little red dots emerged as a distinct population around 600 million years post-creation and underwent a rapid decline around 1.5 billion years later. Their appearance and disappearance seem to trace some fundamental transition in how the universe organized itself. About 70% of the targets showed evidence for supermassive black holes at their centers. These were not small black holes created by dying stars. These were monsters weighing millions of solar masses, existing when the universe barely had time to form anything. Traditional black hole formation theories cannot account for them. Stars need time to form, live, die, and leave behind black hole remnants. Those remnants need time to merge and grow. The timeline is too short, unless dark stars provide the seed. When a dark star exhausts its dark matter fuel, the supporting pressure disappears. The entire million solar mass cloud collapses inward with nothing to stop it. No fusion has occurred, so there is no outward radiation pressure. The collapse is catastrophic and total. Within a cosmologically brief moment, the entire structure plunges past the point of no return and forms a black hole. This black hole starts with a mass already in the millions of solar masses range. It does not need to grow from a tiny seed. It does not need to overcome the Eddington limit, the theoretical maximum rate at which black holes can consume matter. It begins large and can immediately start accreting material from its surroundings without spending eons working its way up from stellar mass. The timing works perfectly. Dark stars form in the first few 100 million years. They shine for perhaps 1 million years, maybe longer with replenishment. Then they collapse into black holes right when JWST observations start detecting impossibly massive black holes in tiny galaxies. The correlation is too strong to ignore. But some little red dots appear in regions that look nearly empty. They sit in voids where there should not be enough matter to feed a growing black hole. Their isolation contradicts everything we thought we knew about how massive black holes form and grow. Anna Christina Eilers at MIT called it perplexing. These quasars are not necessarily in the highest density regions of the early universe. Some seem to be in the middle of nowhere. How do you grow a monster in an empty desert? 25% of the universe is made of something we cannot see, cannot touch, and cannot detect with any instrument that measures light. We call it dark matter, and it is not dark in the sense of being shadowed. It is dark because it does not interact with electromagnetic radiation at all. No wavelength can bounce off it. No telescope can capture its image directly. We know it exists only because galaxies spin wrong. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in spiral galaxies. The pattern made no sense. Stars far from the galactic center were moving just as fast as stars near the center, when they should be moving much slower, according to Newton's laws of gravity. Something invisible was pulling on them, something that outweighed all the visible stars and gas combined. Clusters of galaxies showed the same problem. The gravity needed to hold them together was 5 times stronger than what visible matter could provide. For decades, physicists proposed various candidates for this missing mass. Maybe it was black holes. Maybe it was dead stars too dim to see. Maybe it was exotic particles left over from the Big Bang. Observations gradually ruled out most conventional explanations. Whatever dark matter is, it must be a new type of particle not included in our standard model of physics. The leading candidate is the WIMP. These particles would have mass between 10 and several hundred times a proton, placing them in a sweet spot for explaining dark matter abundance. The name comes from how they interact, weakly, meaning through forces similar to the weak nuclear force that governs certain types of radioactive decay. This is much, much weaker than electromagnetism, which is why WIMPs can pass through normal matter almost without any effect. The elegance of WIMP theory lies in a coincidence that cosmologists call the WIMP miracle. When you calculate how many particles with roughly weak force interaction strength should have survived from the early universe, you get almost exactly the dark matter density we observe today. This is not fine-tuning. It emerges naturally from basic physics. The annihilation rate, the expansion rate of the universe, and the final frozen-out density all connect through equations that give the right answer without any adjustment. Here is how it worked in the early universe. Initially, all particles were in thermal equilibrium, constantly forming and annihilating in the hot cosmic soup. As the universe expanded and cooled, eventually, the temperature dropped below the threshold needed to create new WIMP pairs. Existing WIMPs continued annihilating each other when they collided, causing their numbers to decrease exponentially. But expansion was also reducing the density, making collisions rarer. At some critical moment, the universe expanded fast enough that WIMPs could no longer find each other to annihilate. The process froze out, leaving a relic population that has been drifting through space ever since. The number density got locked in at that moment and has simply been diluted by expansion from then until now. Calculate the freeze-out density using weak force interaction strengths, and you get the dark matter abundance that gravitational measurements require. But confirming WIMP theory requires detecting these particles directly or finding indirect evidence of their annihilation products. Despite decades of increasingly sensitive experiments buried in mines and carved into mountains, no one has caught a WIMP interacting with ordinary matter. Until now, the dark stars might be showing us annihilation in action. Those trillion collisions happening every second inside the early clouds are creating exactly the signatures we are seeing. When two WIMP particles collide, they do not bounce off each other like billiard balls. They vanish. Both particles cease to exist, and their entire rest mass energy converts into other particles according to the rules of quantum field theory. The universe enforces strict accounting. Energy cannot be created or destroyed, only transformed. In this case, mass transforms into a cascade of lighter particles that carry away the energy. The exact products depend on what channel the annihilation follows, but typical outcomes include photons, electron-positron pairs, and neutrinos. Neutrinos barely interact with anything, so they escape the collapsing cloud immediately and carry their energy away into the void. They are lost to the star. But photons and charged particles like electrons get trapped. Picture a photon trying to escape from deep inside a dense hydrogen cloud. It travels a tiny distance before hitting a hydrogen atom, getting absorbed, and then re-emitted in a random direction. The photon takes what physicists call a random walk, zigzagging through the gas in a drunken path that might point inward just as often as outward. The denser the gas, the shorter the distance between collisions, and the longer it takes for energy to work its way out. In the conditions of early dark star formation, the gas is dense enough that photons and electrons deposit essentially all their energy into the surrounding hydrogen before they can escape. The hydrogen atoms absorb this energy and start moving faster. Temperature is just the average speed of particles, so faster moving atoms means higher temperature. The energy that was locked in dark matter mass is now heat in the gas. This heating has a crucial effect. It creates pressure. Hot gas pushes outward with a force proportional to its temperature. As dark matter continues annihilating and dumping energy into the cloud, the temperature rises and pressure increases. Eventually, the outward pressure force becomes strong enough to counteract the inward pull of gravity. The cloud stops collapsing and reaches a stable equilibrium. Calculations show that for 100 GeV WIMPs with standard annihilation cross-sections, this balance occurs at densities far lower than what fusion would require. The cloud never compresses enough to ignite hydrogen burning. Instead, it settles into a puffy, extended structure held up entirely by dark matter annihilation energy. A dark star is born. The power output is staggering. Each annihilation converts mass to energy with 100% efficiency, compared to fusion, which converts less than 1%. The amount of energy released per unit mass is 100 times greater than fusion. Given the high dark matter densities in early universe halos and the continuous replenishment of dark matter falling into the star, the total luminosity can reach billions or tens of billions of times what the sun produces. The process is self-sustaining as long as dark matter keeps flowing in. The star captures dark matter from its surroundings through gravitational pull. That dark matter sinks toward the center where densities are highest. Annihilation rate depends on density squared, so the central regions produce the most power. But unlike fusion stars, the energy generation is spread throughout the entire volume, wherever dark matter particles happen to be, not concentrated in a tiny core. This distributed heating is what allows dark stars to grow so large. They do not have the structural constraint of needing to contain a thermonuclear explosion at their center. They are more like giant light bulbs powered from within, glowing steadily without the dramatic dynamics of fusion-powered objects. But this raises a critical question. Why could not fusion stars form first? Normal star formation follows a well-understood sequence. A cloud of gas begins to collapse under its own gravity. As it contracts, gravitational potential energy converts to heat. The center gets hotter and denser, while the outer layers continue falling inward. Eventually, the core reaches temperatures around 10 million degrees, hot enough for hydrogen nuclei to overcome their electromagnetic repulsion and fuse into helium. The fusion reaction releases energy, creating outward pressure that halts the collapse. A star is born. This process requires specific ingredients that did not exist in the very early universe. The most critical missing component was efficient cooling. For a gas cloud to collapse, it must radiate away energy. If energy cannot escape, pressure builds up and prevents further contraction. In the modern universe, atoms and molecules provide numerous ways to cool. Collisions between particles can excite electrons to higher energy levels, and when those electrons drop back down, they emit photons that carry energy away. But in the pristine gas emerging from the Big Bang, these cooling mechanisms were limited. The universe contained only hydrogen and helium, with trace amounts of lithium. No carbon, no oxygen, no nitrogen, no metals of any kind. The word metals in astronomy means any element heavier than helium, and the early universe was metal-free by definition. These heavy elements had not been created yet, because they form only inside stars through nuclear fusion. Hydrogen can cool through molecular hydrogen formation, where two hydrogen atoms bond together. These molecules can radiate energy through rotational and vibrational transitions. But forming molecular hydrogen requires specific conditions and proceeds slowly. The cooling rate is not efficient enough to allow rapid collapse into dense stellar cores in most circumstances. Without efficient cooling, gas clouds in the early universe would heat up as they contracted, generating pressure that resisted further collapse. The structures that formed would be larger and more diffuse than modern stars, protostellar objects that never quite reached the densities needed for fusion ignition. Some clouds eventually cooled enough to form what astronomers call population 3 stars, the first fusion-powered generation. But this process took time. Dark stars bypass this problem completely. They do not need to compress to extreme densities. They do not need efficient cooling mechanisms. The energy from dark matter annihilation provides the necessary pressure support at relatively low densities. The heating happens from within rather than from gravitational compression, so the cooling rate becomes less important. Dark stars can form in conditions where fusion stars cannot. The timeline matters enormously. JWST is detecting bright objects at redshift 14, corresponding to 300 million years after the Big Bang. This is extraordinarily early. Traditional stellar evolution models suggested we should not see much light from this era because not enough time had passed for efficient star formation. The discovery of these bright early objects created what some scientists called a universe-breaking crisis. If all that light came from fusion stars, it would require impossibly rapid and efficient star formation processes. The mass would need to turn into stars at rates higher than any observed mechanism can explain. Something about our models would be fundamentally wrong. But if much of the light comes from dark stars, the problem vanishes. Dark stars can form quickly, shine intensely, and explain the observations without breaking physics. The evidence keeps pointing in one direction. These early luminous objects are not behaving like star clusters. They are behaving like something we have never seen before. Before galaxies existed, before stars ignited, before planets formed, the universe organized itself on the scaffold of dark matter. In the first moments after the Big Bang, tiny quantum fluctuations in density got stretched to cosmic scales by inflation. These ripples in the distribution of matter and energy seeded all future structure. Dark matter responded to them first. Unlike ordinary matter, dark matter never interacted with the cosmic radiation field in a way that would smooth out structures. Regular matter was tightly coupled to photons in the early universe through electromagnetic forces. Any attempt by normal matter to clump together would be resisted by radiation pressure pushing outward. Dark matter had no such constraint. It felt only gravity, both its own self-gravity and the gravity of the expanding space-time around it. The overdense regions began collapsing. Where dark matter density was slightly higher than average, gravitational attraction pulled in more dark matter from the surroundings. These regions grew denser, which increased their gravitational pull, which accelerated the infall, creating a runaway process. Within a few 100 million years, the first dark matter halos had condensed. A halo is not an object you can see or photograph. It is a region of space where dark matter has accumulated to densities far above the cosmic average. Think of it as an invisible bowl carved into spacetime by gravity, with dark matter particles orbiting and swarming throughout the volume. The densest part sits at the center, with density falling off gradually toward the edges, following what astronomers call a density profile. Simulations show these first halos were small by galaxy standards, perhaps only 10,000 to 1 million times the Sun's mass in total dark matter content. But relative to their size, they were incredibly dense. Dark matter particles were packed together millions of times more tightly than in the universe at large. This high density created ideal conditions for annihilation. Regular matter, still coupled to radiation, could not yet collapse into these halos, but as the universe continued expanding and cooling, eventually the temperature dropped below 3,000 degrees. At that point, electrons and protons combined to form neutral hydrogen atoms in an event called recombination. With neutral atoms came decoupling from radiation. Matter and light went their separate ways. Now hydrogen and helium gas could fall into the pre-existing dark matter halos. Gravity pulled the gas inward toward the deepest potential wells. As it fell, it picked up speed and began to heat from compression. The gas settled into the central regions of the halos, forming dense clouds that would become the first protostellar objects. But before fusion could ignite, dark matter annihilation started heating these clouds from within. The halo environment was perfect for dark star formation. You had high dark matter density, providing abundant fuel. You had pristine hydrogen and helium gas, providing the observable material. You had gravitational wells deep enough to trap the annihilation products. All three necessary conditions existed simultaneously in a way that would never repeat once heavy elements began polluting the gas and altering the cooling properties. These mini-halos, as cosmologists call them, were the wombs of cosmic dawn. Inside them, the universe experimented with its first luminous structures. Some halos might have formed dark stars. Others might have formed early fusion stars through different mechanisms. Many probably did nothing interesting and simply merged with larger structures later. But the halos that did create dark stars left signatures we are only now beginning to detect. The densest concentrations produce the most spectacular results. One object in particular has captured intense scientific attention. Among the 4 dark star candidates identified in the initial JWST survey, one stands out. Scientists labeled it with a technical designation that encodes its position on the sky and its discovery survey. But what matters is not its name. What matters is a single line in its spectrum, an absorption feature at 1,640 angstroms that should not be there if this were a normal galaxy. Spectroscopy is astronomy's most powerful tool. By spreading light into its component wavelengths, you can determine what atoms and molecules exist in distant objects, how hot they are, how fast they are moving, and what processes are generating their light. Every element leaves a unique fingerprint, a specific pattern of lines where light gets absorbed or emitted. By reading these fingerprints, astronomers decode the composition and behavior of objects billions of light years away. When Cosmin Illy examined this particular candidate's spectrum, he immediately recognized its significance. The absorption feature matched predictions for supermassive dark stars almost exactly. Normal galaxies do not show this pattern. The wavelength corresponds to helium transitions that occur under very specific temperature and density conditions that match the outer layers of a dark star, but not the stellar populations of early galaxies. This is what scientists call a smoking gun, a piece of evidence so specific and unusual that it points to only one explanation. In this case, the explanation is that we are looking at an object powered by dark matter annihilation rather than fusion. The theory predicted this signature years before JWST launched. Now, observation has confirmed it exists in at least one target from the early universe. Additional observations using the Atacama Large Millimeter Array, a ground-based radio telescope in Chile, detected oxygen in the vicinity of this object. Oxygen is a heavy element created only inside stars through nuclear fusion. Its presence means that either some fusion stars form nearby, or this dark star exists in a region where a regular galaxy has already polluted the gas with metals. Either way, the environment is more complex than a simple isolated dark star. One possibility is that the dark matter halo merged with a small galaxy, combining dark star formation with conventional stellar populations. Another possibility is that dark stars and fusion stars formed simultaneously in the same halo, with dark matter annihilation heating some gas clouds, while molecular hydrogen cooling allowed others to collapse into fusion objects. The early universe was chaotic, with different formation mechanisms competing and sometimes cooperating. But the presence of metals does not invalidate the dark star interpretation. It actually strengthens the case by showing that the environment is consistent with early galaxy formation scenarios where multiple processes occurred in close proximity. The key point is that the spectral signature remains, unexplained by conventional stellar physics and matching dark star predictions remarkably well. This single object has become the focal point of intense study. Every available instrument is being pointed at it to gather additional data. The team is working to automate the search process, using machine learning algorithms that can scan through thousands of JWST spectra looking for similar patterns. If dark stars were common in the early universe, more candidates should exist in the data. Finding a dozen or more would transform this from an intriguing possibility into an established phenomenon. The implications extend far beyond confirming a theoretical prediction. If we have found dark stars, we have found direct evidence of dark matter annihilation in action. We have opened a window into the nature of the mysterious particles that dominate the universe's mass budget. We might finally be seeing the invisible made visible through its effects on the first luminous structures. The universe begins as a point of infinite density and temperature, expanding outward in a violent explosion that creates space and time itself. In the first fractions of a second, fundamental forces separate from each other. Particles and antiparticles appear and annihilate in a roiling plasma where temperatures exceed trillions of degrees. This is the Planck era, when quantum mechanics and gravity merge in ways we still do not fully understand. As expansion continues, the universe cools rapidly. Within microseconds, quarks bind together to form protons and neutrons. Within minutes, nuclear fusion begins creating helium from hydrogen in the primordial soup. By the time the universe is 20 minutes old, the abundance of light elements has been set. Roughly 75% hydrogen, 25% helium, with trace amounts of lithium. This ratio will persist until stars begin forging heavier elements billions of years later. For the next 380,000 years, matter and radiation remain coupled in an opaque fog. Photons cannot travel far before scattering off free electrons. The universe is essentially a glowing cloud, bright everywhere but transparent nowhere. Then recombination occurs. Electrons and nuclei combine to form neutral atoms, and suddenly, light can travel freely. The cosmic microwave background we detect today was emitted at this moment. Now comes the Dark Age. No stars exist yet. No galaxies have formed. The universe contains only neutral gas and dark matter, slowly organizing itself under gravity's patient pull. This era lasts for approximately 100 million years, a period when the cosmos is truly dark, lit only by the fading afterglow of the Big Bang. At 300 million years, we reach the epoch when JWST is detecting its brightest early objects. This is still incredibly early by cosmic standards. The universe is only 2% of its current age. For comparison, if the cosmos today were a 50-year-old person, we are looking at events from their first year of life. The structures forming now are the seeds of everything that comes later. Temperatures have dropped to a few dozen degrees above absolute zero in most regions, though collapsing gas clouds are heating up through compression. The expansion rate is still very high, meaning structures must form quickly to avoid being diluted into irrelevance. Dark matter halos have condensed in the overdense regions, creating gravitational wells that are starting to trap hydrogen and helium gas. The environment is harsh and chaotic. When halos collide and merge, shock waves heat the gas to millions of degrees. When gas falls into halos, it releases gravitational energy that can power intense radiation. The first generation of stars, whether dark stars or fusion stars or both, is beginning to light up the darkness. Their ultraviolet light starts re-ionizing the neutral hydrogen, creating bubbles of ionized gas that grow and eventually overlap. This era, called cosmic dawn, represents one of the most important transitions in universal history. Before cosmic dawn, the universe is cold, dark, and structureless. After cosmic dawn, galaxies begin forming, stars create heavy elements, and the stage is set for planets and eventually life. We are witnessing the birth of complexity from simplicity. The objects JWST sees from this epoch are not minor curiosities. They are the pioneers, the first structures to achieve brightness in a previously dark cosmos. Understanding how they formed and what powered them is essential to understanding how we got from the Big Bang to the rich, structured universe we inhabit today. And the evidence increasingly suggests that dark matter played a direct role in cosmic dawn. Inside a collapsing gas cloud in the early universe, specific numbers determine what happens next. Temperature measures the average energy of particles. Density counts how many particles occupy each cubic centimeter of space. Together, these two quantities control whether a cloud forms a dark star, a fusion star, or nothing at all. The boundaries between these outcomes are sharper than you might expect. For fusion to ignite, the core of a collapsing cloud must reach approximately 10 million degrees. At lower temperatures, protons lack sufficient energy to overcome electromagnetic repulsion and merge. Below this threshold, no matter how long you wait or how much mass you accumulate, hydrogen burning cannot begin. The temperature requirement is absolute, set by nuclear physics. Achieving 10 million degrees requires compressing gas to enormous densities, typically around 100 grams per cubic centimeter in the core. For reference, water has a density of 1 gram per cubic centimeter, so stellar cores are 100 times denser than water. The compression heats the gas through the conversion of gravitational potential energy into thermal energy. You cannot get hot enough for fusion without getting dense enough first. Dark stars operate in completely different conditions. Their cores might reach only a few 100,000 degrees, far below fusion threshold. Their densities can be as low as a billionth of a gram per cubic centimeter, roughly the density of our Sun's outer atmosphere. These conditions are too gentle for fusion, but perfect for dark matter annihilation to dominate as an energy source. The key difference is cooling efficiency. In the early universe, hydrogen clouds could radiate energy through molecular hydrogen formation and subsequent emission from those molecules. But this cooling process is slow and inefficient compared to modern star formation, where heavy elements provide many additional cooling channels. Without efficient cooling, clouds heat up as they collapse and eventually reach a point where pressure prevents further contraction. This is where dark matter annihilation changes the game. The heating from annihilation occurs throughout the cloud's volume, not just at the center. It provides support against gravitational collapse without requiring high densities. The cloud settles into an equilibrium state, where dark matter heating balances radiative cooling and some continued slow collapse. This equilibrium exists at densities far too low for fusion, but sufficient for maintaining a stable structure. Calculations show that for typical dark matter halo conditions in the early universe, this equilibrium temperature would be in the range of a few thousand to a few 100,000 degrees, depending on the dark matter particle, mass, and annihilation cross-section. The corresponding density would be low enough that the structure remains puffy and extended, potentially reaching sizes larger than Earth's orbit around the Sunday. This explains why dark stars can grow so massive. A fusion star is constrained by the need to maintain hydrostatic equilibrium against a concentrated nuclear furnace. It must balance immense central pressures with structural integrity. As fusion stars add mass, they become more unstable. The most massive stars are constantly flirting with catastrophic disruption. There is an upper limit to how big a fusion star can grow before it tears itself apart. Dark stars face no such constraint. The heating is distributed, the structure is stable, and adding mass simply means incorporating more volume into the glowing cloud. They can grow to millions of solar masses while remaining structurally sound. The limits on their size come from dark matter supply and competition with other formation mechanisms, not from internal instabilities. These specific conditions existed for only a narrow window of cosmic history. Once heavy elements began polluting the gas and improving cooling efficiency, fusion star formation became easier and dark star formation became less favorable. The era of dark stars ended, but their remnants might still exist. When JWST began returning its first deep field images, astronomers experienced a mixture of excitement and confusion. The telescope had delivered on its promise, revealing galaxies from the earliest cosmic epochs with unprecedented clarity. But the properties of these galaxies made no sense according to conventional formation models. They were too bright, too numerous, and too mature for their age. Standard galaxy evolution theory predicts a gradual buildup of stellar mass over time. Small proto-galaxies form first, merge with each other, and gradually assemble into larger structures. Star formation efficiency should be relatively low in the early universe because the gas has not yet been enriched with heavy elements. Without metals, cooling is inefficient, and star formation proceeds slowly. By this logic, the first billion years should produce relatively faint, irregular structures, not the bright, well-organized galaxies JWST was detecting. The observations told a different story. Galaxies at redshift 10, corresponding to about 450 million years after the Big Bang, were shining as brightly as galaxies billions of years older. Some appeared to contain stellar populations, equivalent to billions or tens of billions of solar masses. The mass-to-light ratios were wrong, the colors were wrong, the sheer number of bright early galaxies exceeded predictions by factors of 10 to 100. Some scientists initially suggested this meant our cosmological model was broken. If the standard expansion history and dark matter framework could not explain these observations, perhaps fundamental assumptions needed revision. The phrase universe-breaking entered the discourse. Headlines proclaimed that JWST had disproven the Big Bang or falsified dark matter. The reality was more subtle and more interesting. The issue was not with cosmology itself, but with how astronomers had modeled galaxy formation within that cosmological framework. The models assumed all early light came from fusion stars. If a significant fraction actually came from dark stars, the problem dissolved. Dark stars can achieve enormous luminosities very quickly, without requiring the slow buildup of stellar populations that fusion-powered galaxies need. A single dark star with 1 million solar masses and 10 billion solar luminosities contributes as much light as an entire small galaxy. If early halos were producing dark stars alongside or instead of conventional stellar populations, the observed brightness could be explained without invoking exotic physics. The mass budget works. The timeline works. The spectral properties roughly match depending on the mix of dark stars versus fusion stars. This interpretation gained support from spectroscopic studies, showing that many early bright objects had unusual characteristics. Gas motions were faster than expected. Chemical abundances were peculiar. Some objects appeared to have massive black holes at their centers far too early. All these oddities aligned with a picture where dark stars formed, evolved, and collapsed into black holes on rapid timescales, seeding the growth of the first quasars. The little red dots, discovered in early JWST data, fit this narrative perfectly. They are compact, extremely luminous, and show evidence for accreting black holes. Their red color comes from dust obscuration combined with cosmological redshift. Their high abundance matches predictions for dark star formation rates in the early universe. Their decline around 1.5 billion years after the Big Bang corresponds to when conditions became less favorable for dark star formation. Instead of breaking the universe, JWST observations were revealing a previously hidden chapter of cosmic evolution. Dark stars represented a transient phenomenon, important during cosmic dawn but fading away as conditions changed. We are seeing their signatures now because we finally built a telescope capable of observing the universe at that early epoch. The pristine clouds of hydrogen floating in darkness were waiting for something to ignite them. Imagine gas that has never been touched by starlight, never passed through a stellar furnace, never been processed by any mechanism except the primordial nuclear fusion that occurred in the Big Bang's first minutes. This is the starting material for everything that comes later. Roughly 75% hydrogen by mass, 25% helium, with lithium making up a few parts per 10 billion. Nothing else exists. The hydrogen is in its simplest form, a single proton orbited by a single electron. The helium consists of 2 protons, 2 neutrons, and 2 electrons. These atoms are the building blocks, pristine and unmodified, spreading through the expanding universe as neutral gas. They carry no memory of previous stellar generations, because there have been no previous stellar generations. This is the first act. These clouds are enormous by any human scale, often spanning thousands of light years across and containing masses equivalent to hundreds of thousands or millions of suns. But they are diffuse, with densities lower than the best laboratory vacuum we can create on Earth. Particles are separated by centimeters or meters on average, drifting through space in near-perfect isolation, except when they occasionally collide. Gravity is patient. It pulls gently but relentlessly on every particle, drawing them toward regions where mass has already begun to accumulate. The dark matter halos provide the gravitational scaffolding, invisible frameworks that guide the motion of ordinary matter. Gas falls along streams toward the densest points, forming filaments and eventually concentrating into the cores of halos. As the gas falls inward, it speeds up. Gravitational potential energy converts to kinetic energy, meaning the atoms move faster. When fast-moving atoms collide, their kinetic energy can be converted to other forms, primarily thermal energy and radiation. This is how cosmic structures heat up during formation. The faster you fall, the harder you hit when you arrive, and the more energy gets released. In some clouds, conditions allow molecular hydrogen to form. 2 hydrogen atoms bond together, creating the simplest molecule in existence. This molecule can radiate energy through rotational and vibrational transitions, providing a cooling mechanism that pure atomic hydrogen lacks. The cooling allows further collapse, which increases density, which accelerates molecular formation in a positive feedback loop. These clouds might eventually compress enough to ignite fusion and become population 3 stars. But in other clouds, dark matter density is high enough that annihilation begins before molecular cooling can take over. The energy released by annihilating WIMPs heats the gas from within, preventing the runaway collapse toward fusion conditions. The cloud reaches an equilibrium where it remains diffuse and extended, but hot enough to shine brightly. A dark star forms instead. The chemical purity of these clouds is essential to the process. Even a tiny amount of heavier elements would drastically alter the cooling properties and potentially prevent dark star formation by allowing the gas to collapse more efficiently. The narrow window when pristine gas coexisted with high dark matter densities could not last forever. Once the first generation of stars began producing heavy elements and dispersing them through supernova explosions, the environment changed fundamentally. This is why dark stars are a phenomenon of the very early universe. They require conditions that existed only before stellar enrichment began contaminating the gas. They are a one-time occurrence in cosmic history, never to be repeated. The clouds that formed them were special, existing in a brief window between the end of the Dark Age and the beginning of significant metal production. Those special clouds were responding to invisible forces, pulling them together in the depths of space. The universe does not stay the same. Every second, space itself expands, stretching the distances between galaxies and cooling the cosmic background radiation. This expansion is not objects moving through space. It is space growing, carrying everything along with it. The rate of this expansion determines what structures can form at any given time. In the first moments, expansion was so rapid that nothing stable could exist. The universe doubled in size countless times in tiny fractions of a second during inflation. Then, expansion slowed to a still rapid but more moderate pace. Matter and energy were too hot and energetic to form stable structures. Particles appeared and disappeared in the plasma. Nothing permanent could condense out of the chaos. As expansion continued and temperatures dropped, particle interactions slowed. Quarks formed protons and neutrons. Protons and neutrons formed light nuclei. Eventually, electrons joined nuclei to make atoms. Each phase transition occurred when the universe cooled below a critical temperature, where the binding energy of the new structure exceeded the average particle energy. Below that temperature, structures became stable. Above it, they remained impossible. The Dark Age began when atoms formed and lasted until the first luminous objects appeared. During this period, the universe was expanding at a rate determined by its total energy density, which was dominated by dark matter and ordinary matter, with some contribution from radiation. The expansion rate set a timescale. How quickly did densities decrease due to dilution versus how quickly did structures grow through gravitational attraction? Structures that collapsed faster than the expansion rate could overcome dilution and grow. Structures that collapsed slower got spread out and disappeared. The critical scale depended on the mass of the overdense region and the era when it was collapsing. In the first few 100 million years, only dark matter halos below a certain mass could collapse quickly enough to become bound structures. Larger potential galaxies had not had time to fully condense yet. This is why the first luminous objects formed in small halos. They were the fastest to collapse because they had the highest initial overdensities. These mini-halos became the sites of cosmic dawn, where gas accumulated and formed the first dark stars or fusion stars. Only later did larger structures fully assemble. Temperature evolution also played a crucial role. The cosmic background radiation cooled according to the expansion rate, dropping from thousands of degrees at recombination to a few dozen degrees by 300 million years post-Big Bang. This cooling affected the gas temperature everywhere, providing a baseline that local heating or cooling mechanisms then modified. In regions where gas was falling into halos, temperatures could rise to thousands or even millions of degrees from shock heating. In regions where molecular hydrogen was forming efficiently, temperatures could drop below the cosmic average. The interplay between cosmic expansion, cooling, gravitational heating, and various localized processes created a complex temperature landscape. Dark matter annihilation added another heat source to this mix. Its importance depended critically on the local dark matter density, which was highest in halo cores. As the universe expanded and structures grew, average dark matter densities decreased. Annihilation rates, which depend on density squared, dropped rapidly. The era when annihilation could power dark stars was limited to the period when dark matter densities remained extremely high. All these factors combined to create a narrow window of cosmic history when dark stars could form and shine. That window is now closing forever, but something massive is about to collapse from the weight of these giants. Dark stars cannot shine forever. Their power source is finite, limited by the amount of dark matter available in their immediate surroundings. The annihilation process consumes dark matter particles at a rate determined by their density and collision frequency. Every annihilation removes 2 particles permanently. Eventually, the supply runs low. The original dark matter trapped inside a dark star, when it formed, might last approximately 1 million years. This sounds like a long time, but it is brief on cosmic scales. For comparison, a fusion star like our Sun will burn for 10 billion years. Dark stars live fast and die young, blazing brilliantly for a cosmological instant before their fuel vanishes. During its lifetime, a dark star can capture additional dark matter from its environment. The gravitational pull extends far beyond the visible boundary of the glowing hydrogen cloud. Dark matter particles passing nearby get deflected and potentially captured into orbits around the star. If they pass close enough to the dense central regions, they lose energy through interactions and become gravitationally bound. This replenishment could extend the dark star's lifetime significantly, potentially allowing it to shine for tens of millions of years under ideal conditions. But replenishment cannot continue indefinitely. Dark matter halos themselves are dynamic structures that evolve through mergers and interactions. When two halos collide, their contents get stirred and redistributed. A dark star sitting peacefully at the center of its halo might suddenly find itself displaced to the outskirts, where dark matter density is much lower. Once displaced, the replenishment rate drops dramatically. When the dark matter density falls below a critical threshold, annihilation can no longer generate enough power to support the structure. The heating rate decreases, temperature drops, pressure falls. Without sufficient pressure to counteract gravity, the collapse resumes. What happens next depends on the mass and structure at that moment. If the dark star has incorporated enough hydrogen and helium through continued accretion, it might have accumulated millions of solar masses of ordinary matter. This gas has been held up by dark matter annihilation pressure, prevented from collapsing into the high densities needed for fusion. The support was artificial, maintained only by the continuous injection of energy from annihilation. When that support disappears, nothing remains to prevent catastrophic collapse. The entire cloud begins falling inward under its own gravity. There is no fusion to create outward pressure. There is no radiation to push back against infalling material. The collapse is free and unimpeded, accelerating rapidly as the structure contracts. Within a matter of hours or days, material that was spread across distances larger than Earth's orbit around the Sun plunges into a region smaller than our solar system. The density increases by factors of trillions. Space-time itself begins to curve dramatically under the concentrated mass. The escape velocity at the surface exceeds the speed of light. An event horizon forms. The dark star has become a black hole, but this is not a small, stellar mass black hole of the type formed when massive stars explode. This is a black hole that starts with a mass of 1 million suns or more. It is already in the supermassive category, born fully grown without needing billions of years to accumulate mass through slow accretion. This solves one of the most perplexing mysteries in modern cosmology. JWST keeps finding monsters that should not exist. Black holes, weighing millions or billions of solar masses, appear in galaxies that formed less than a billion years after the Big Bang. These supermassive black holes power quasars, the brightest sustained sources of light in the universe. Their existence raises a fundamental question that has troubled astrophysicists for decades. How did they grow so large so quickly? The problem is one of time and feeding rates. Black holes grow by consuming matter from their surroundings. Gas, dust, and occasionally entire stars fall into the gravitational well, releasing enormous energy as they spiral inward through the accretion disk. But there is a limit to how fast this process can occur, a speed limit set by physics itself. That limit is called the Eddington rate, named after Arthur Eddington, who derived it nearly a century ago. When matter falls onto a black hole, friction in the accretion disk heats the material to millions of degrees. This superheated gas radiates intensely, especially in ultraviolet and X-ray wavelengths. The outward pressure from this radiation pushes against infalling material, creating resistance to further accretion. If a black hole tries to consume matter faster than the Eddington rate, the radiation pressure becomes so strong that it blows away the incoming material. The black hole essentially chokes on its food. It cannot force feed itself beyond this limit, without expelling the very gas it is trying to consume. For a black hole of given mass, you can calculate the maximum accretion rate, and therefore the maximum growth rate over time. Start with a stellar mass black hole formed from a dying star, perhaps 10 to 100 solar masses. Let it accrete at the Eddington limit continuously, without interruption. Calculate how long it takes to reach 1 million solar masses. The answer comes out to hundreds of millions of years at minimum, often longer when you account for realistic complications. But JWST detects million solar mass black holes at redshift 10, just 450 million years after the Big Bang. Some appear even earlier. A black hole discovered at redshift 13.1 existed only 430 million years after creation. The timeline is impossibly tight. Even feeding at the absolute maximum rate from the moment of formation, a stellar mass seed cannot grow large enough, fast enough. You can try to rescue the conventional picture by invoking special circumstances. Maybe these black holes fed at super Eddington rates through some exotic mechanism we do not fully understand. Maybe they had unusually abundant gas supplies that somehow overcame radiation pressure. Maybe the early universe was different in ways that changed the Eddington limit. Each explanation requires special pleading and stretches the physics. Or you can start with a much heavier seed. If the initial black hole already weighs 1 million solar masses, it does not need to grow much at all. It starts in the supermassive category and can immediately begin powering a bright quasar. The timeline problem vanishes. This is the heavy seed scenario, and it requires a formation mechanism that can produce massive black holes directly without going through stellar evolution. Dark stars provide exactly this mechanism. When they collapse, they create black holes with masses set by the total amount of hydrogen and helium that had accumulated in the dark star structure. If the dark star reached 1 million solar masses before its dark matter fuel ran out, the resulting black hole inherits that mass instantly. No growth period needed, no Eddington limit to overcome. The supermassive black hole appears fully formed. The correlation between dark star predictions and observed early black holes is striking. Dark stars should form in the first few 100 million years, exist for roughly 1 million years, then collapse. We should see bright objects at redshift 14 to 10, followed by massive black holes appearing shortly after. JWST sees exactly this pattern. The monsters are not paradoxes. They are fossils of a dark star era. Picture a black hole surrounded by a disk of swirling gas. The gas spirals inward, orbiting faster and faster as it approaches the event horizon. Friction between adjacent layers of the disk converts orbital energy into heat. The inner regions reach temperatures of millions of degrees and glow brilliantly in X-rays. This accretion disk can outshine entire galaxies, powered purely by the gravitational potential energy of matter falling into the black hole. But the brightness creates a problem. Light carries momentum. When photons emitted by the hot disk strike gas particles in the outer accretion flow, they transfer momentum and push the gas outward. This radiation pressure opposes the inward pull of gravity. For a given black hole mass and accretion rate, you can calculate whether gravity wins or radiation wins. Arthur Eddington worked out the mathematics in the early 20th century. He showed that for any spherically symmetric accretion onto a compact object, there exists a critical luminosity above which radiation pressure exceeds gravitational attraction. If you try to accrete faster and generate more luminosity, you simply blow away the infalling material. The limit is fundamental, arising from the balance between gravity and electromagnetism. The Eddington luminosity depends directly on the black hole mass. More massive black holes have stronger gravity and can therefore accrete faster before hitting the limit. But the mass doubling timescale is still measured in tens of millions of years, even under optimal, continuous Eddington rate accretion. Starting from a 10 solar mass seed, you need at least 30 mass doubling times to reach 10 million solar masses. That requires hundreds of millions of years of continuous, uninterrupted, maximum rate feeding. Real black holes do not accrete continuously. Gas supplies fluctuate. Feedback effects can temporarily shut down accretion when powerful outflows clear gas from the surrounding region. Mergers and interactions disrupt the orderly accretion flow. When you include realistic complications, growth timescales become even longer. Models that start from stellar mass seeds and follow their growth through cosmic history consistently fail to produce enough massive black holes early enough to match observations. Theorists have explored various ways to exceed the Eddington limit. Perhaps some black holes accrete through geometries that are not spherically symmetric, allowing radiation to escape along certain directions, while matter continues flowing in from other angles. Perhaps extremely dense gas streams can penetrate deep into the potential well before radiation pressure becomes effective. Perhaps magnetic fields channel material in ways that bypass the standard limits. These mechanisms might work under specific circumstances and could contribute to faster than Eddington growth for brief periods. But sustaining super Eddington accretion for millions of years requires extraordinary fine-tuning of conditions, and even doubled or tripled Eddington rates do not solve the timeline problem for the earliest, most massive black holes JWST has detected. The heavy seed scenario cuts through this complexity. If you start with a million solar mass black hole from a collapsed dark star, it does not need to exceed Eddington limits at all. It can grow leisurely, accreting gas at standard rates, or even sub-Eddington rates, and still match the observations. The initial mass head start is so enormous that subsequent growth becomes almost irrelevant for explaining the earliest quasars. This is not just about numbers fitting observations. It is about having a physically plausible formation pathway that does not require multiple improbable conditions, all occurring simultaneously. Dark stars forming in early halos, shining for their brief lifetimes, then collapsing into massive black holes is a natural sequence that emerges from basic physics. The evidence keeps accumulating that nature chose this path during cosmic dawn. In theoretical astrophysics, direct collapse refers to the formation of a black hole without an intermediate stellar phase. Normal stellar evolution proceeds through a sequence. Gas cloud collapses, fusion ignites, the star burns for millions or billions of years. Fusion fuel exhausts, and only then does the core collapse into a compact remnant. Direct collapse skips all the middle steps. For direct collapse to occur, you need a massive gas cloud that can implode catastrophically without ever igniting fusion. This requires suppressing the nuclear reactions that would normally stabilize the structure and convert it into a star. In the modern universe, this is nearly impossible. Gas clouds naturally fragment as they collapse, breaking into smaller pieces that individually reach fusion conditions. Heavy elements provide efficient cooling that accelerates fragmentation. The end result is always star clusters, not single massive collapsing objects. But the early universe offered different conditions. With only hydrogen and helium present, cooling was inefficient and fragmentation was suppressed. Massive clouds could remain intact during collapse. However, they would still heat up from compression, eventually reaching temperatures where fusion would ignite. Direct collapse to black holes remained difficult even in the primordial environment, unless something provided additional support to prevent compression to fusion densities, while still allowing overall gravitational binding. Dark matter annihilation provides exactly this. It heats the cloud just enough to maintain pressure support at relatively low densities. The structure remains stable for cosmologically significant timescales. Then, when annihilation shuts off due to dark matter depletion, the support vanishes and collapse proceeds unimpeded. This is direct collapse with a twist. The cloud does go through a luminous phase as a dark star, but this phase does not involve fusion and does not fundamentally alter the collapse dynamics. When the transition occurs, the entire million solar mass structure implodes, essentially at freefall velocity. Within hours, material crosses the Schwarzschild radius, and an event horizon forms. The process is as direct as you can get, while still allowing the object to be visible before it collapses. Simulations of dark star collapse show that the process is remarkably clean. The structure does not fragment or produce multiple smaller black holes. The implosion is coherent, with all material falling inward along radial trajectories. The final black hole mass equals the initial dark star mass to within a few percent. Some material might be ejected in the form of relativistic jets or winds, but the bulk becomes part of the black hole. This scenario predicts specific signatures that observers could potentially detect. There should be a population of transient events corresponding to dark stars collapsing in real time. Each collapse would produce a characteristic signature, rapid dimming as the luminous cloud disappears inside the event horizon, possibly accompanied by a burst of gravitational waves as the black hole rings down to its final equilibrium state. Current telescopes might not be sensitive enough to catch these events, which would be extremely rare and distant, but future facilities with wider fields of view and better time domain coverage could spot them. Finding even a handful of dark star collapse events would provide smoking gun confirmation of the entire formation pathway. The implications extend beyond just explaining early black holes. If direct collapse through dark stars was common, it means the seeds of today's supermassive black holes have a fundamentally different origin than anyone expected. Every giant black hole at the center of every major galaxy might trace its lineage back to a dark star that collapsed 13 billion years ago. The ancient monsters ruling galactic centers today were born from invisible matter, destroying itself in the cosmic dawn. Black holes do not remain isolated forever. Gravity draws them together over cosmic timescales. When two black holes orbit each other closely enough, they radiate gravitational waves that carry away orbital energy. The orbit shrinks, the black holes spiral inward, and eventually they collide and merge into a single, larger black hole. This process, confirmed by gravitational wave detectors in recent years, plays a crucial role in building supermassive black holes. If dark stars commonly formed in the early universe and collapsed into million solar mass black holes, these black holes would have become the nuclei of small proto-galaxies. As those proto-galaxies merged through gravitational interactions, their central black holes would have been brought together. The merger of 2 million solar mass black holes creates a 2 million solar mass black hole. Merge that with another million solar mass hole, and you get 3 million. The addition is straightforward. But mergers do more than simply add masses. They also kick the resulting black hole in a random direction through momentum conservation. Gravitational wave emission during the final moments of merger is not perfectly symmetric. The waves carry more momentum in some directions than others, and conservation laws require the merged black hole to recoil in the opposite direction. These kicks can reach velocities of hundreds or even thousands of kilometers per second. In small proto-galaxies with relatively weak gravitational potential wells, these kicks could eject the black hole entirely. The merged black hole would be flung out of its host galaxy, wandering through intergalactic space. This sounds like it would deplete galaxies of their central black holes, but the effect is more subtle. Ejected black holes do not disappear. They carry their mass with them and remain gravitationally bound to the larger scale structure. Over time, these wandering black holes settle back into gravitational potential wells, often merging with other wandering black holes or finding their way to the centers of larger galaxy assemblages. The net effect is to concentrate black holes in the deepest potential wells, which correspond to the most massive galaxies. This produces exactly the correlation we observe in the modern universe. More massive galaxies harbor more massive central black holes. The merger cascade also explains the timing of quasar activity. Quasars are brightest when black holes are actively accreting gas at high rates. Mergers trigger inflows of gas toward galactic centers by disrupting the orderly motions that kept gas in stable orbits. The chaotic gravitational environment during a merger funnels gas inward, feeding the central black holes and powering bright quasar emission. JWST observations show that many early galaxies appear to be in the process of merging or have recently merged. The disturbed morphologies, tidal tails, and multiple nuclei visible in high-resolution images all point to frequent interactions. This merger-rich environment would have been ideal for building up massive black holes through the cascade process. Starting with heavy seeds from collapsed dark stars dramatically shortens the timescale for reaching billion solar mass black holes. Instead of needing hundreds of millions of years of continuous accretion, you need only a few tens of merger events. Each merger can be completed within a few million years, from initial orbital decay to final coalescence. 10 mergers of million solar mass seeds produces a billion solar mass black hole in roughly 100 million years, easily fast enough to explain the earliest quasars. The gravitational wave background generated by these mergers should be detectable with pulsar timing arrays, experiments that use the galaxy as a gravitational wave detector by precisely measuring the arrival times of pulses from distant pulsars. Early hints of this background have already been reported, though confirmation requires more data. Every piece of evidence points toward dark stars seeding a merger cascade that built the supermassive monsters ruling galaxies today. For decades, the story of cosmic dawn followed a simple narrative. First came dark matter halos. Then gas fell into those halos. Then the gas cooled and fragmented into clumps. Then those clumps collapsed to high enough density to ignite fusion. Then the first stars were born. These population 3 stars were massive and short-lived, producing the first heavy elements through nuclear reactions. They exploded as supernovas, enriching their surroundings with metals. This enrichment allowed later generations of stars to form more easily, eventually leading to galaxy formation and everything that followed. This narrative assumes that fusion stars were the first luminous objects. Dark stars append this assumption. If dark matter annihilation could power luminous objects before fusion became possible, then the first lights in the universe were not stars in the conventional sense. They were dark stars, hybrids of ordinary matter and exotic particles, shining through a fundamentally different energy generation mechanism. The implications are profound. The chemical enrichment history of the universe might need revision. If dark stars dominated early luminosity, they did not produce heavy elements because they never underwent fusion. The metals that enabled later star formation had to come from a different source, probably from true fusion stars that formed slightly later. The sequence of events becomes more complex and interesting. Cosmic reionization, the process by which the universe transitioned from neutral to ionized hydrogen, might have been driven partially or primarily by dark stars, rather than population 3 stars. Dark stars could have produced copious ultraviolet radiation, capable of ionizing surrounding gas. Their large sizes and high luminosities would have made them extremely effective at carving out ionized bubbles in the neutral hydrogen fog. The timeline of structure formation might need adjustment. If dark stars formed in smaller, denser halos than fusion stars, they could have appeared earlier and in different locations. The spatial distribution of early luminous objects would reflect dark matter halo properties more directly, without the filtering effects of gas cooling and fragmentation that affect fusion star formation. Galaxy formation theories, built on the assumption that stellar feedback drives much of the evolutionary process, might be incomplete. Dark stars do not explode as supernovas. They do not produce strong stellar winds. Their feedback is primarily through the heating and ionization of surrounding gas by their radiation, not through mechanical energy injection. If dark stars were common, the early galaxy environment was gentler than models assuming population 3 supernovas predict. This does not mean fusion stars were absent or unimportant. Most evidence suggests that both dark stars and fusion stars coexisted during cosmic dawn, forming in different environments or at different times within the same halos. The relative importance of each population remains an open question that JWST observations are beginning to constrain. But the possibility that dark stars came first and dominated early luminosity forces a rethinking of basic assumptions about how structure emerged from the primordial darkness. The universe's first light might have come from invisible matter destroying itself, not from atomic nuclei fusing together. The dawn of cosmic dawn was darker than we imagined. Dark matter has haunted physics for nearly a century. We know it exists. We can measure its gravitational effects. We can map its distribution through gravitational lensing and galaxy dynamics. But we have never detected a single dark matter particle directly. It remains the ultimate invisible actor, shaping the universe while refusing to show its face. Every attempt to directly catch a dark matter particle has failed. Deep underground detectors shielded from cosmic rays wait for a WIMP to collide with a xenon or germanium nucleus, producing a tiny recoil signal. Decades of searching with increasingly sensitive instruments have yielded nothing definitive. The parameter space where WIMPs could hide continues shrinking as experiments set ever tighter limits on interaction cross-sections. Particle colliders have also come up empty. The Large Hadron Collider was partly built to discover supersymmetric particles that could serve as dark matter candidates. After years of operation and thousands of collisions, no convincing signals have emerged. Either dark matter particles are heavier or interact more weakly than hoped, or they are not the type of particles that colliders can produce at all. Indirect detection through annihilation products has been similarly frustrating. Searches for excess gamma rays from galactic centers or satellite galaxies have produced hints and anomalies, but nothing conclusive. Every promising signal eventually gets explained by more conventional astrophysical processes. The dark matter signature remains elusive. Dark stars offer a completely different approach. Instead of trying to detect individual particles in controlled experiments, we look for the collective effects of enormous numbers of particles annihilating in the early universe. The signal is not a few scattered photons or a single nuclear recoil. It is entire stars shining across cosmic distances, powered by dark matter heating. The scale of the phenomenon makes it detectable in ways that individual particle interactions are not. If the dark star interpretation of JWST observations is correct, we are seeing dark matter annihilation in action. The spectrum, luminosity, and evolution of these objects encode information about the dark matter particle properties. The annihilation cross-section determines how much power gets generated per unit volume. The particle mass affects the temperature and size of the resulting dark stars. The nature of the annihilation products influences the detailed spectrum. By studying dark stars as a population, astronomers can constrain dark matter properties through stellar archaeology rather than particle physics experiments. The constraints might not be as precise as laboratory measurements would provide, but they are independent and complementary. They probe dark matter behavior under conditions that can never be replicated in terrestrial experiments. Extreme densities in the early universe, when particles were much more likely to interact. Catherine Fries has argued that identifying supermassive dark stars opens a new field of astronomy focused on dark matter-powered objects. This field would use telescopes and spectroscopy rather than particle detectors to study the invisible substance that dominates the universe's mass budget. The techniques are completely different from traditional dark matter searches, but the goal is the same: understanding what dark matter is and how it behaves. The cosmic irony is remarkable. The invisible becomes visible through its effects on the visible. Dark matter, which refuses to emit or absorb light, becomes detectable by making clouds of hydrogen shine. The shadow reveals itself by casting light. Anna Christina Eilers and her team use JWST to study the environments surrounding 5 of the earliest known quasars. These blazing beacons exist at redshifts between 6 and 7, formed when the universe was between 600 and 700 million years old. Every conventional model predicted they should be embedded in dense regions packed with gas and proto-galaxies. The observations told a different story. Some quasars showed exactly the expected environment: rich fields with numerous companion galaxies, abundant gas streams, and obvious signs of ongoing mergers. These systems made sense according to standard formation theories. The black holes had plenty of material to feed on and could plausibly have grown through continuous accretion from their surroundings. But other quasars appeared to sit in voids. Their surroundings were surprisingly empty of companion galaxies and lacked the dense gas concentrations needed to feed a growing black hole. The term "middle of nowhere" appeared in the scientific papers. How can a black hole weighing millions or billions of solar masses exist in a region with minimal matter density? The paradox deepens when you consider that black holes require continuous feeding to power quasar-level luminosity. A bright quasar converts matter into energy at rates equivalent to consuming several solar masses per year. Without a steady supply of gas, the accretion disk empties quickly and the quasar shuts off. Isolated quasars should be fading rapidly, yet many show no evidence of dimming. Dark star collapse provides a natural explanation. If a dark star formed in what was initially a dense dark matter halo, it would shine brightly during its annihilation-powered phase. But halos are not static. They move through space, interact with other halos, and respond to large-scale gravitational flows. A halo that was dense when the dark star formed might have been disrupted by tidal forces from nearby structures by the time the dark star collapsed. When the dark star collapses into a black hole, the resulting quasar appears in whatever environment the halo happens to occupy at that moment. If the halo has been stripped of much of its gas through interactions, the quasar finds itself isolated. It can continue shining for a while by consuming the remaining gas in its immediate vicinity, but it lacks the massive reservoirs that would allow sustained high luminosity accretion. This scenario predicts that some early quasars should appear isolated, exactly as observations show. It also predicts that these isolated quasars should be relatively young, recently formed from dark star collapse, rather than having grown through long periods of accretion. As more JWST data becomes available, checking this prediction by measuring quasar ages and comparing isolated versus embedded systems will be possible. Another possibility involves dark star mobility. If dark stars formed slightly offset from halo centers, or if mergers displaced them, they might have collapsed in regions that appear empty from large distances, even though the overall halo structure remains intact. The resolution limits of JWST might not be sufficient to detect the diffuse gas that is actually present close to the quasar. Both explanations involve dark stars, and both differ fundamentally from conventional quasar formation scenarios. The isolated quasars are not anomalies or failures of theory. They are natural outcomes of a dark star formation pathway. Their existence strengthens rather than weakens the case for dark stars as heavy black hole seeds. The emptiness surrounding some early monsters is not a mystery to be explained away. It is a signature of their exotic origins. Among the 4 dark star candidates initially identified from JWST data, one stands out for its extreme distance. Spectroscopic measurements place it at redshift 14, corresponding to light that has traveled for over 13 billion years. When this light was emitted, the universe was only 300 million years old, roughly 2% of its current age of 13.8 billion years. Redshift 14 is not the current distance record, but it ranks among the most distant confirmed objects with detailed spectroscopy. The light we receive from this object has been stretched by a factor of 15 through cosmic expansion. Ultraviolet photons emitted at the source appear as infrared light by the time they reach JWST's detectors. This extreme stretching means that even hot, bright objects appear very red and faint. Detecting an object at this distance requires extraordinary sensitivity. The signal is incredibly weak after traveling across most of the observable universe. Foreground galaxies can block or distort the light. Cosmic rays can mimic faint point sources. Separating genuine detections from instrumental artifacts or foreground contamination requires careful analysis and multiple confirmations. JWST's spectroscopic capabilities made this detection possible. Rather than relying solely on imaging in multiple filters, which can be ambiguous, the telescope split the light into its component wavelengths. The resulting spectrum shows absorption and emission features at specific wavelengths determined by atomic physics. These features are redshifted by exactly the amount corresponding to the expansion of the universe between emission and detection. The spectrum of this redshift 14 object shows characteristics that do not match any known type of galaxy. The emission lines are too weak for the overall luminosity. The continuum shape is wrong for a stellar population. The absorption feature at 1,640 angstroms, the potential dark star smoking gun, appears clearly despite the object's faintness. Everything about the spectrum suggests something exotic. If this is truly a dark star, it represents the earliest known example. 300 million years after the Big Bang is remarkably soon for any structure to form. Dark matter halos at this epoch would have been quite small, perhaps only hundreds of thousands of solar masses. Yet somehow, a massive dark star managed to form and shine brightly enough to be detected across cosmic distances. The early formation time has implications for dark matter properties. To produce observable dark stars, this quickly requires efficient dark matter concentration in the first halos. The particle physics parameters must fall in a narrow range, where annihilation is strong enough to power dark stars, but weak enough that too much dark matter did not annihilate away in the very early universe, before structures formed. This object also provides the longest look-back time for studying dark stars. If the dark star interpretation is correct, we are seeing the phenomenon very close to its beginning. The pristine conditions at 300 million years represent the optimal environment for dark star formation. Later times involve more contamination from heavy elements and more disruption from mergers and feedback. The detection pushed JWST to its limits. Fainter, more distant dark stars might exist, but remain beyond current capabilities to detect and characterize. Future instruments with greater collecting area or better spectral resolution will be needed to push the frontier further back toward the cosmic dark age. But this single detection at redshift 14 proves that JWST can see back to cosmic dawn and resolve individual luminous objects from that era. The universe's infancy is no longer hidden behind an impenetrable veil. When JWST first revealed massive bright galaxies at high redshift, some scientists worried that cosmology itself might be wrong. If galaxies form too quickly, too massive, and too mature for their age, perhaps the Big Bang model needed revision. Perhaps dark matter was not real. Perhaps the expansion history of the universe differed from what cosmic microwave background measurements indicated. Headlines proclaimed that JWST had broken the universe. The concern was not entirely unreasonable. The standard cosmological model, called lambda CDM, makes specific predictions about structure formation. Dark matter collapses into halos. Baryonic matter falls into those halos. Stars form through gas cooling and fragmentation. Galaxies build up gradually through hierarchical mergers. Each step takes time, and the total timeline from Big Bang to galaxy formation is constrained by the expansion rate and growth of structure. If observations showed mature galaxies with billions of solar masses in stars at redshift 12 or 15, the timeline would be impossibly short. There would not have been enough time for hierarchical assembly to produce such massive systems. The observations would contradict the model in a fundamental way that could not be explained by tweaking parameters within the standard framework. But dark stars resolve this apparent contradiction. The bright objects JWST detected do not need to be galaxies full of fusion stars. They can be single, dark stars or small groups of dark stars. each shining as brightly as billions of suns. The mass in stars can be much lower than the total luminosity suggests, because the mass-to-light ratio for dark stars is so different from fusion-powered stellar populations. When you reanalyze the observations, assuming a mix of dark stars and fusion stars rather than fusion stars alone, the tension with cosmological models disappears. The required stellar masses drop to levels that hierarchical assembly can easily produce. The formation timescales become consistent with standard structure formation theory. The apparent crisis was an interpretation problem, not a fundamental failure of cosmology. This resolution is elegant because it requires no modification to the underlying physics. Lambda CDM remains intact. The expansion history stays the same. Dark matter properties do not need adjustment. All that changes is recognition that dark matter can directly power luminous objects under the conditions present in the early universe, something that theorists predicted years before JWST launched. The little red dots that appeared impossible to explain as galaxies make perfect sense as dark stars or as small galaxies hosting massive black holes formed from collapsed dark stars. Their red colors, compact sizes, rapid evolution, and unusual spectra all emerge naturally from dark star theory. What looked like a crisis becomes a discovery. This episode illustrates both the robustness and the limitations of cosmological models. The models correctly predict that bright objects should exist in the early universe, but they struggle to identify what type of objects would dominate early luminosity. Dark stars represent a gap in the models, a phenomenon that should have been included from the beginning, but was not widely considered until observations forced the issue. Going forward, simulations of early galaxy formation will need to incorporate dark star physics alongside fusion star formation. The relative importance of each mechanism probably varied with environment, halo mass, and cosmic time. Understanding this interplay will require sophisticated models that track both dark matter and baryonic matter through cosmic evolution. The universe is not broken. It is stranger and more interesting than we realized. The 4 dark star candidates identified so far are likely just the beginning. JWST has surveyed only a tiny fraction of the sky, and most of its data has not yet been analyzed with dark star detection as a primary goal. Catherine Fries and her collaborators are developing automated search algorithms that can scan through thousands of spectra, looking for the characteristic signatures that human analysts would take years to find manually. Machine learning offers powerful tools for this task. Train a neural network on simulated dark star spectra and known galaxy spectra, then let it classify real observations. The algorithm can process data far faster than humans and might identify subtle patterns that visual inspection would miss. Early tests show promising results, with automated searches recovering known candidates and flagging additional objects of interest. Expanding the search will require telescope time, which remains the most precious commodity in astronomy. Every major observatory is oversubscribed, with far more proposed observations than available hours. Convincing time allocation committees to dedicate significant resources to dark star searches requires strong preliminary evidence that the phenomenon is real and scientifically important. The initial detections provide that evidence, opening the door to more extensive follow-up campaigns. Future observations will focus on several goals. First, confirming that candidate objects are truly dark stars by obtaining higher resolution spectra that definitively rule out alternative explanations. Second, measuring the abundance of dark stars as a function of redshift to trace their evolutionary history. Third, searching for dark star collapse events or their immediate aftermaths to catch the transition from dark star to black hole. Fourth, looking for dark stars in different environments to understand what conditions favor their formation. Other telescopes will contribute to the effort. The Atacama Large Millimeter Array can detect molecular emission from gas surrounding dark star candidates, revealing their immediate environment. The The Chandra X-ray Observatory can search for X-ray emission from accretion onto newly formed black holes created by dark star collapse. Gravitational wave detectors might eventually catch signals from black hole mergers involving dark star remnants. Ground-based extremely large telescopes coming online in the next decade will have collecting areas several times larger than JWST, allowing them to detect even fainter objects from even earlier times. These facilities will push the dark star search toward redshift 15 and beyond, approaching the absolute earliest moments when luminous structures could have formed. The long-term goal is to construct a complete census of dark stars across cosmic history. How many formed? When did they appear and disappear? What were their typical masses and luminosities? How did they influence their surroundings through radiation and eventual collapse? Answering these questions will require decades of observations across multiple wavelengths using various facilities, but the payoff is extraordinary. If dark stars are confirmed as a major population in the early universe, they become a new tool for studying both cosmology and particle physics. Their properties constrain dark matter particle mass, annihilation cross-section, and distribution. Their abundance tests models of structure formation. Their collapse provides the heavy seeds for supermassive black holes that conventional theories cannot explain. The first dark stars shone 13 billion years ago and vanished after brief lifetimes measured in millions of years. They existed in conditions that will never be repeated, powered by processes we are only beginning to understand. Now, after traveling across most of the observable universe, their light has finally reached us. We are seeing echoes of cosmic dawn, reflections of a time when invisible matter made the first lights shine. The universe keeps its secrets for billions of years, but eventually everything comes into view. The dark stars waited in the ancient past until we built instruments capable of seeing them. They were always there. We just needed to look far enough back into the darkness to find where the first light came from.